The recent surge of attention surrounding Comet 3I/Atlas has grown significantly after new telescope images revealed an unexpected and dramatic transformation in its appearance, especially in the structure of its ion tail. This interstellar comet, only the third of its kind ever detected passing through our solar system, has already been a subject of intense interest among astronomers, but the newest observations have elevated that curiosity to a new level. Captured on November 10th by Italy's Virtual Telescope project using robotic instruments based in Manciano, the latest image consists of 18 carefully compiled long exposures that, when combined, offer one of the clearest and most detailed views of this comet to date. In the composite photo, the comet displays a sharply extended ion tail that is both brighter and longer than seen in any earlier measurements, suggesting a sudden spike in activity as it interacts more strongly with the sun's radiation and the solar wind. According to astronomer Gianluca Massi, the founder and lead scientist of the Virtual Telescope project, the rapid enhancement of the tail indicates that Comet 3I/Atlas is undergoing intensified physical changes as it travels closer to the inner regions of the solar system. This observation could provide astronomers with a rare opportunity to analyze how an object formed around another star behaves under the energetic influence of our Sun for the very first time. The formation of an ion tail is a complex process involving the interaction between the comet's escaping gases and the stream of charged particles emitted by the Sun. As 3I/Atlas approaches the Sun, its icy materials, frozen gases, and volatile compounds that have remained untouched since the early history of its original star system begin to heat up and sublimate, meaning they transform directly from solid to gas. When this gas escapes from the nucleus, ultraviolet radiation from the Sun strips electrons from the molecules, converting them into ions. These newly formed ions respond to the pressure of the solar wind, the constant flow of charged particles blowing outward from the Sun at high speed. This causes the ions to be swept away from the comet's nucleus, forming a long, narrow, often bluish tail that always points directly away from the Sun, regardless of the comet's direction of travel. While a comet typically has two tails, a dust tail and an ion tail, the ion tail is more sensitive to solar conditions and can change rapidly in brightness and shape. The sudden extension observed in 3I/Atlas implies a significant increase in the amount of ionized material being released into space, possibly due to the exposure of new volatile-rich layers beneath the comet surface as it heats up. 3I/Atlas holds a special place in modern astronomy because interstellar objects are extraordinarily rare. Before it, only 2 confirmed interstellar visitors had been documented: the elongated, mysterious Oumuamua in 2017 and the more traditional Comet 2I/Borisov in 2019. Oumuamua sparked scientific controversy because of its unusual shape, lack of a visible tail, and extremely brief observation window, which made it difficult to study in detail. In contrast, 3I/Atlas is a bright, active comet with observable emissions, allowing researchers to analyze its composition and physical behavior far more precisely than they could with Oumuamua. Its brightness at the current stage of its journey means that ground-based telescopes around the world can study it without relying solely on space-based instruments. This accessibility gives astronomers a unique chance to examine material that formed around another star, possibly billions of years ago, using the tools available here on Earth. The growth of the ion tail has drawn attention not only because of its visual impact, but also because of what it suggests about the comet's internal composition. A dramatic increase in the tail's brightness implies that the comet is releasing larger amounts of gas, potentially including substances such as carbon monoxide or carbon dioxide, which are highly responsive to sunlight and capable of producing strong ion emissions. As these gases flow outward and react with solar radiation, they carry with them chemical signatures of the environment in which the comet originally formed. By studying the wavelengths of light emitted by the ionized gases, astronomers can derive clues about the molecular makeup of the comet's nucleus. These clues can help reconstruct the physical conditions of the star system, where 3I/Atlas began its long journey, offering insight into how planets and smaller bodies form in different parts of the galaxy. In many ways, interstellar comets act as time capsules, preserving primitive materials from their birthplaces in a nearly unchanged state. What makes this event even more scientifically valuable is the fact that 3I/Atlas is experiencing this level of activity during its first recorded encounter with our Sun comets that originate within our solar system typically go through many perihelion passages, meaning they repeatedly approach the Sun over long periods. Each encounter strips away some of their volatile material, leaving behind a nucleus that becomes gradually less active over time. But interstellar comets, like 3I/Atlas, may be experiencing such heating and sublimation for the first time in millions or even billions of years. This means the gases and ices emerging from the comet now may include components that have been sealed deep within it since the earliest stages of its formation. Observing these materials as they come into contact with the solar wind allows astronomers to study pristine, ancient cosmic chemicals that are nearly impossible to sample by any other means. The sudden growth of the ion tail may also hint at more dramatic internal processes taking place within the comet. Rapid heating can cause thermal stress inside the nucleus, potentially leading to fractures or localized explosions of activity. When a comet experiences such internal stress, jets of gas may erupt from its surface with greater force, dramatically increasing the amount of material expelled into space. These jets can alter the shape of the tail, cause the comet to brighten unexpectedly, and even change its trajectory slightly. If 3I/Atlas continues to increase in brightness and activity, further observations may reveal structural evolution in the nucleus itself, including surface cracks or new active regions releasing gas at high velocity. Such changes could help scientists better understand how interstellar comets respond to the stresses of entering a new star's gravitational and thermal environment. Another intriguing aspect of the comet's behavior is what it implies about the star system from which it originated. The composition of its gases, the relative abundance of different volatile molecules, and the nature of the dust particles in its coma can all offer insight into the chemical makeup of its home environment. Astronomers are particularly interested in whether interstellar comets contain the same types of organic compounds and complex molecules found in comets native to our solar system. If they do, this would suggest that the building blocks of life, such as carbon-rich molecules, are widespread throughout the galaxy, strengthening the idea that planetary systems everywhere may share similar origins. If, on the other hand, the composition of 3I/Atlas is significantly different from that of solar system comets, this could reveal how diverse planetary formation can be depending on local conditions, temperatures, and the presence or absence of certain elements. The growth of the tail also provides a way to study the solar wind itself. By observing how the tail bends, stretches, or shifts direction, astronomers can track variations in the speed and density of the charged particles flowing from the Sun interstellar comets, with their unusually active ion tails, act as natural probes of space weather conditions, giving researchers a way to map the invisible forces that shape our solar system. The structure of the tail can reveal moments of intensified solar activity, such as solar storms or magnetic field fluctuations. In this sense, studying 3I/Atlas does not only teach us about the comet, it also improves our understanding of the environment through which the Earth moves. In the coming months, astronomers expect to continue monitoring the comet closely as it moves deeper into the inner solar system. If its activity continues to increase, it may produce even more dramatic displays, including further stretching of the ion tail or unexpected bursts of brightness. Each new observation will add to the growing picture of how interstellar objects behave under solar heating, helping researchers refine models of cometary physics. Whether 3I/Atlas eventually fades quietly into the distance or surprises observers with even more energetic outbursts, its presence offers a rare and fascinating window into the ancient past of another star system.